Okay, finally, we are moving on to the last topic of this notebook, transcendental functions. Here we are going to review exponential and logarithmic functions and some trigonometric functions. We are going to key upon equations because in order to solve an equation, we have to use everything we have learned so far and then put together to get it done. First, let's review exponential and logarithmic rules. And here's one. Log and exponential cancel each other. Exponential and log cancel each other because they're inverse functions. Some special cases. Log of 1 is 0. Log of e is 1. E to the 0 power is 1. Everything to the 0 power is 1, by the way. E to the first power is e, and so on. And also, let's see. If you have infinities, then you can use graphical approach to determine whether that's infinity is going to positive infinity or negative infinity. Okay, we are finally ready to open the graph here. Okay, let's go. Exponential logarithmic functions here. So e to the 0 power is 1, log of 1 is 0, e to the first power is e, and log of e is 1. We see those from those 4 dots. And the horizontal asymptote, e to the negative infinity is going to 0, e to the positive infinity going to positive infinity. Over here, log of infinity, this is slowly but going up, so infinity. Log of 0, where 0 plus, that's going down to negative infinity. We can see all these from these graphs. Okay, and then the log rules. One more comment. These are common mistakes. Please be careful. Log times log is not log of x times y, and so on. Let's move on to some examples of logarithmic equations. Here they are. Let's see. Probably we will not have time to do all these, so let's take some of them. For example, this one is going to be just too easy. And this is a linear equation, isn't it? Solve for 2 to the 3x plus first power. Solve it, and then take the log, and then you're going to get what? Never mind. Let's just open up and let's talk about it. Solve for 2 to the 3x plus first power, and then take the log, and the 3x plus 1 comes out from log rule number 3. And then this is just a linear equation again. Solve for x, and that's going to be our solution. What if we have two exponentials? If I divide one from the other, then we can combine these into a single logarithm. How do I do that? Simply subtract the powers. And what do we have? This exponential equals a number, so all you have to do is to take a logarithm, and then you're going to have a linear equation. Pretty simple from that point on. How about we have two exponentials, but another constant here? That kind of thing, this constant would have caused trouble in this kind of problem, because if I divide, then I have, well, I'll create another exponential. However, if we use alternative trick, sometimes this can be done, because this is very simple. E to the x power, e to the 2x power, that's basically e to the x squared. Basically, this is a quadratic equation. So you can factor and then solve for 2 to the e to the x power. What do we have? Negative 1/3 and then 3/2. The first one is invalid because exponential is always positive. Taking a log of the second one, I'm going to get log of 3/2. Be careful about extraneous solutions, even more so for logarithmic equations, by the way. How about the next one? This is going to be quadratic equations too, because 4 is 2 squared. So this is 2 to the x squared, basically. How do we take care of 2 to the x plus first power? Not just 2 to the x power. Okay, I'll leave that to students. It'll turn out to be a quadratic function again, quadratic equation, and factorization again. Alright, let's move on to logarithmic equations. If you have a single log, that's pretty simple. All you have to do is solve for logarithm and then take the exponential. Here we go. Solve for log and take the exponential. All I have to do now is solve for x. That was easy. Actually, no. This is not complete, I'm afraid. Well, okay. this is not the end, because logarithmic functions have very small domain. So whenever you have x value or candidate of x value, you have to plug it back into the original equation and see if that's right, as a matter of fact. So this is 2 log of 3 times plugging this one back in. So that's 1. So 3 times 3, so this is times 3. And then there was plus 1, wasn't it? That is equals to -3. We have to find out if that is true. So 3 times 1/3, okay, that's going to cancel out. And -3/3 plus 1, that's going to cancel out. And what do we get here? E to the -3 halves power, okay. Using the log rule, I can take that one out. So, okay, so we get that. And the 2 and 2 cancel out. And is that right? Yes, it is. Log of E is 1. -3 times 1 is -3. Okay, that's right. So you always have to check for extraneous solution, because sometimes you just have no solution. I neglected that part in this notebook, so I'll make the addition and post the correct one in Blackboard. I'm recording this sometime in June, so by the time you're taking this course, corrected one will be up there. Okay, let's move on to the next problem. We have logarithmic equation this time with 2 logarithms. How do we handle that? You can use the log rule to change this log plus log into log of a times b form. So you can combine it to a single logarithm like this. And the right hand side, getting 2 upstairs, we get 3 squared. What do we have now? Log of a equals log of b form. By taking exponential of both, we can simply kill off the log. And what do we have? We have a quadratic equation. Solving this is easy. And then we have a couple of candidates. Now, it is very, very important that you checked for the extraneous solution. I neglected that in previous problem, and this time I did not forget. Plug in, and then what do we have? This is invalid. Log of negative, that's invalid. Plug in x equal to 4, that's okay. So we have one solution, x equals to 4, and this will turn out to be extraneous. You'll have to cross it out. This checking process is absolutely necessary for logarithmic equations. Final problem in this part, again, taking these log minus log into a single logarithm is the first step. You can use a quotient. And then 2 goes upstairs, and then we have 3 squared. What do we end up with? Taking the exponential of both, we can kill off the log, and then we just end up with fraction equation. This can be changed into usual linear equation, and then we have an answer, x equal to 12/17. But don't stop here. Make sure you plug this back into the original equation. I apologize again, I just neglected in this problem. I didn't neglect this time and that time. Plug in, do the computation. Is it right? It turns out it is correct. So, oh, no, excuse me, it is not correct. This turns out to be negative, so this equation has no solution at all, no real solution. Okay, this kind of thing happens actually. It's pretty frequent. Luckily, in this problem I neglected, that didn't happen, but this time it did happen, so no solution here. Again, I cannot emphasize this too much. Check for extraneous solutions, especially for logarithmic equations. Now let's move on to trigonometric functions. These are trigonometric identities. I kind of rearranged them in the order of importance. I used to call this one number 1. Now I changed my mind actually. Close number 2 here now took number 1 spot. Tangent is sine of a cosine. And then there are some other reciprocal identities too. Cosecant is 1 over sine, secant is 1 over cosine, cotangent is 1 over tangent, consequently cosine over sine. Okay. Pythagorean identity, cosine squared plus sine squared equals to 1. Very close number 2. And using Pythagorean identity and those reciprocal identities, you can actually deduce the other and the other identities here. As a matter of fact, this is what you're going to end up with. So start from here, divide everything by cosine squared. Divide by cosine squared. And then divide this one too by cosine squared. And then simplify. Cosine over cosine, that's 1. Sine over cosine, that's tangent. So we have tangent squared here. 1 over cosine, that's secant. So what do we have? We were able to deduce the second identity from the first one. I can do the same thing by dividing everything by sine squared to get the third one. So this is what I encourage actually. Instead of trying to memorize everything, just memorize the several key ones and then deduce the others from using your critical thinking skills actually. That's more desirable. Double angle formula, which is very, very important too. Here they are. And here, solving for cosine squared and also solving for sine squared, we get these two identities. Some people call it half angle formula, some people call it double angle formula, some people call it power reduction formula, whatever the name is, these are all important. Sum and difference identity, I didn't list them here, it's too complicated and you don't really use it for calculus level, calculus 1 level, so I didn't list it, but please review. These, on the other hand, are a little less well known, but they are very, very important. If you have a sine equation, cosine equation, or tangent equation, what do? Solve for that and then identify what sine of x is. Let's suppose you did that. And how do you find out what x is? Easy. Simply take the arc sine. And then you have this 2k pi because sine is periodic function. Is that enough? No. Pi minus of that is also a solution, and then of course we need this 2k pi. Here is a graphical justification. Let's suppose we have this m value arbitrarily given, and then solve, and then what do we get? Taking arc sine, we are going to get this x coordinate value of this blue point. That's not all. Pi minus of that is automatically a solution, this red one. Now that I have two solid points in a standard domain, I can add 2 pi, add another 2 pi, add another 2 pi to get a second pair, third pair, fourth pair, and so on, left hand side and right hand side. What about cosine? Cosine is actually a little bit easier. Cosine is an even function, so take arc cosine, I get one solution. Minus of that is also a solution, so we have a pair. Add 2 pi, we have another pair. Another 2 pi, we have another 2 pi. And then plus 2 pi again, we have another pair, and so on. Finally, tangent equation. Tangent has periods just pi, so you don't really have to do the second one. Just add 2k pi and then, add k pi, not 2k pi, and that's it. So here we go. Let's use these to solve a trig equation. I think we'll have time to do only just one. Okay, let's go ahead and do one. How about, say, this one? Sine squared plus 3 cosine of x minus cosine squared plus 1 equals to 0. And you can reduce this into quadratic equation. But how? This is a key. 3 cosine of x, that's where everything is going. This is cosine squared, so it's already quadratic term, that's fine. How about sine squared? You can use this Pythagorean identity to change it into 1 minus cosine squared. Here's a solution, by the way. Sine squared is now 1 minus cosine squared. Manipulate it, and you end up with trigonometric function of a cosine function. And then factoring and everything, you can get cosine of x is -1/2 or cosine of x is 2. Cosine of x equals to 2 is going to be invalid because cosine is between -1 and 1. So you can always come back to this one and then find out a couple of values. 2 pi over 3 and 4 pi over 3, or 2 pi over 3 and -2 pi over 3, the equivalent, and then plus 2k pi, and then we can cover everything. 4 pi over 3 will be covered by -2 pi over 3 plus 2 pi, so 2k pi will cover everything.